Pluto is far from the Sun and makes solar energy about 1,500 times dimmer than Earth's, resulting in extremely cold temperatures. At night, the temperature can drop to around -230 degrees Celsius and rise to -170 degrees Celsius during a heat wave. It also has a very delicate feel. Welcome, curious minds, to exploration beyond the known dimensions of our solar system. What if I told you that Pluto, a distant and enigmatic dwarf planet, could make a cosmic move, possibly colliding with none other than the ice giant Neptune? Pluto's rebellious nature was evident from the start, a renegade in our celestial neighborhood whose orbit boldly intersects with another planet, defying conventional norms of planetary behavior. I suggest that this is not the behavior of the planet. From the astonishing complexity of Pluto's orbit to the serious concerns raised by astrophysical luminaries like Neil deGrasse Tyson and Michio Kaku about the cosmic balance, the persistent question hovers: are these celestial giants interacting on a collision course? Could the convergence of these paths bring unexpected results to our dear planet Earth? Today we embark on a cosmic journey full of uncertainty. While the answers to these celestial questions may elude us at first, the possibility of a collision of such cosmic proportions is a stark reminder that the universe is a stage for both inspiring and perhaps somewhat frightening events. Join us as we explore the mysteries surrounding our understanding of Pluto and Neptune and consider the possibility of a celestial conflict that could alter the cosmic balance of our solar system. The stage is set, and the unfolding drama invites us to witness the enigmatic dance of the planets among other possible cosmic events. There are many heads in space, and among them is a complex puzzle called the three-body problem. Scientists predict various possible cataclysms in the celestial theater. Despite the fact that a collision between a planet and another in space is extremely unlikely, it is still not completely out of the question. Gravitational interactions, determined by the three-body problem, are one of the forces affecting planetary orbits. An example of a space system where gravitational forces create a periodic pattern called orbital resonances is TRAPPIST-1, which has 7 Earth-sized planets. Over time, these patterns can destabilize planetary orbits and increase the likelihood of collisions. The current scenario does not involve collisions, despite the fact that systems like TRAPPIST-1 are very dense and the planets influence each other's course, especially when they are close. Scientists often follow these systems to better understand how the planets move through space. Another unknown component is rogue planets that drift aimlessly in space rather than in stellar orbit. Expulsion of planets from star systems can occur due to gravity or other astronomical phenomena such as nearby stars or dynamic instabilities in systems with more than one planet. Over time, these orbiting planets can travel incredible distances and reach regions far from their origin. It's possible they'll cross paths with other star systems on their solo journey. The probability of a planetary collision increases when such planets migrate to another solar system. Although a planet directly colliding with another planet is unlikely given the vastness and often empty space of space, the rarity of planets in open space and the measurement of interstellar distances work together to prevent frequent collisions. A collision between two rogue planets is already very unlikely, but the frequency of rogue planets is much lower than that of stars and planets in fixed orbits. The star systems involved may become chaotic in the event of a galactic merger. Planetary collisions during these cosmic events are particularly unlikely due to the great interstellar distances. The orbits of stars and planets in merging galaxies change dramatically under the influence of strong gravitational forces. A planet could become a renegade world without any stars if such chaos forces it into the cold, black depths of intergalactic space. Alternatively, these gravitational perturbations could cause the planets to be knocked out of their orbits, collide with each other, or even crash into their host stars. When gas and dust are compressed at very high pressures, the gravitational rearrangement can cause new celestial bodies to form or even start the formation of stars. The late heavy bombardment of our solar system indicates that comet and asteroid collisions became more frequent about 4 billion years ago. This increase in shocks is thought to be due to gravitational disturbances caused by the outer planets. During this chaotic segment, gas giants like Jupiter and Saturn wandered around, disturbing the orbits of several smaller bodies in the Kuiper belt and asteroid belt. As a result, these smaller objects were thrown on unpredictable paths, and many ended up in the inner solar system. This flood greatly increased the impact on the terrestrial planets, including Earth. Although these collisions did not involve direct collisions between planets, they illustrate how gravitational interactions can cause significant changes in the orbits of celestial bodies. This bombardment is thought to have played an important role in shaping the surfaces and geological history of the planets in our solar system. In addition, it could have contributed to the supply of water and organic materials to the Earth and influenced the development of our planet in the long term. As the mass of the stars changes, so can the orbits of the planets around them. This is especially noticeable in systems where the stars are at the end of their lives. As a star ages and uses up its nuclear fuel, its mass often undergoes significant changes, especially during phases such as the red giant phase or when it releases material into the planetary nebula. These variations in stellar mass can significantly affect the gravitational balance of the system, causing the orbits of nearby planets to either shift outward or compress. This is more likely to occur in multiple star systems, where complex gravitational interactions can easily lead to unstable orbits. In such systems, the gravitational forces of multiple stars can interact unpredictably, increasing orbital displacements and increasing the possibilities of orbital crossings. This can lead to conditions where planets can be captured by another star, collide with other celestial bodies, or even be thrown into interstellar space. Originally recognized as a full member of the planetary family, Pluto's unique orbit was reclassified and later called a dwarf planet because of its own orbit. The astrophysics community is still excited about it and finds it exciting even with this revision. We are still concerned about the closeness of the Pluto-Neptune path. According to recent predictions by renowned scientists such as Neil deGrasse Tyson and Michio Kaku, these scientists are sounding the alarm about a major threat to Earth, the possibility of an interplanetary collision.
Pluto is unlike any other planet in our solar system, and that's what makes its orbit around the Sun so unique. Pluto has not completed a complete revolution since its discovery in 1930, and its orbit takes 248 years. The fact that it deviates significantly from the circular orbits of the larger planets makes its path exceptionally elliptical. In addition to its rapid rotation, Pluto also has a steeper orbit than the other planets, with an inclination of 17 degrees to the plane of the ecliptic. Pluto's orbit is complicated by the combination of its elliptical shape and inclination. The point where Pluto's orbit intersects Neptune's orbit is an interesting feature. For about 20 years in each orbit, Pluto is closer to the Sun than Neptune, defying expectations based on their position in the solar system. This begs the question, why didn't a Pluto-Neptune collision occur? The explanation lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery, presenting challenges to astronomers. Unlike most planets, whose orbits are relatively close to the ecliptic plane, Pluto's unique features are its steep inclination and elliptical shape. The mystery deepened after realizing that the orbit of Pluto exceeds that of Neptune. The three-body problem helps explain why Pluto's orbit remains stable amid their complexity, a testament to the complexity of celestial mechanics. Understanding the motions and gravitational interactions of three celestial bodies, such as Pluto, Neptune, and the Sun, is known in space as the three-body problem. Projecting these trajectories of the initial position and the effect of gravity on each other is difficult. For Pluto, several factors contribute to solving this astronomical puzzle, including the mean motion resonance, the Kozai mechanism, and the Laplace resonance. According to astrophysicists, the mean motion resonance is crucial because it keeps the planets in orbit. When Pluto crosses the orbit of Neptune, it is at least 90 degrees away from Neptune, a critical distance that prevents collisions. This definition has been applied to Pluto and Neptune, the distance clearances associated with the vertical motion of the celestial body in its orbit ensure that when Pluto approaches Neptune or other large planets, it is well above their orbital plane, providing an additional layer of protection against collisions. A key factor in understanding the motion of the sky is the Laplace resonance, named after Pierre-Simon Laplace, who studied the gravitational interactions between three space objects, including Pluto, Neptune, and the Sun. The goal is to predict the consequences in their orbit and the impact on their orbit. The three-body problem in space is a central topic for astrophysicists, covering a wide range of orbital dynamics and gravitational effects between celestial bodies. Understanding the stability and interaction of systems like Pluto, Neptune, and the Sun requires a careful analysis of their trajectories and the possible influence of their gravitational fields on each other. These complexities highlight the challenges and uncertainties associated with predicting the long-term behavior of planets and other celestial bodies in our solar system and beyond.